Hello everyone, I'm Human Hard Drive, and today on our AVRC tutorials we're going to be delving back into interrupts. Remember that last time we talked about the basic structure of interrupts for AVR. Today we're going to be talking about using timers to generate interrupts to do stuff. So, pretty simple. So with that, let's go ahead and get started. For this you're obviously going to need the datasheet to look at all the registers and such. I've got Atmel Studio open with a new project, just called this one 8-bit timer, because that's what we're going to be starting with. And I do also recommend you use this online calculator. It's a really useful online calculator to do some of the timing calculations, but we'll get to that in a moment. I will put a link to this site in the description. Again, really useful. Frank's website. Okay, so with that, let's go ahead and get started. Now, the AVR, or the ATmega 328P that we're using, has 3 timers. It has 2 8-bit timers and a 16-bit timer. Now, we're going to be dealing with the first 8-bit timer, right here. And it works like this. You've got a timer which counts based on the number of clock cycles plugged into a prescaler, which we'll talk about shortly, which is this value here. And it's compared to a value you give it, which is another register. And when they equal each other, it does something. And so that's what we're going to write our code to do. Now, if I come down here, let's start talking about the registers. Now, what we need to do is we need to create a timer that will generate an output every so often. Let's call it 1 output a second. And we're just going to do that by turning an LED on and off. Now to do that, remember this is an 8-bit timer. That means the max value we can ask it to time out is to 8 bits. Now that's 255 clock cycles. That's with the direct clock. Now this is where the calculator comes in. We're using a 20 megahertz clock with 8-bit resolution. Now, I mentioned prescalers. What a prescaler will do is it'll take that input clock, our 20 megahertz clock, and divide it by a certain number. So you can divide it by 8, 64, 256, or 1024. So if we were to just use one clock, if we were to use the pure clock on an 8-bit timer, and we were to fill out all 255 ticks, that comes down to a little more than 1,000th of a second. So not all that much time. If, however, we were to use a max prescale of, say, 1024, we would then get about 1 second. We could get 1 second out of the clock using a prescaler of 1024. So that's pretty good. Now, that's a little more. If we were to, say, ask it for 1 second, that works out to... I was off in my calculation. There we go. 20, 1, 2, 3, 1, 2. That's not 20, that's 20 megahertz. Let's try that again. If we were to just use the pure clock with 255 ticks, we would get, that's the number I was expecting. There we go. Much less than 1,000th of a second. I apologize for that. For the proof, I can't count. So that's with just a pure clock. With only 255 ticks, we can only get something in the range of a 10,000th of a second, 100,000th of a second. Yeah, 100,000th of a second. If we were to use the max prescaler of 1024, that's dividing each tick, or it reduces each tick to 1,024th of a tick. So it'll only increment every 1,024 clock cycles. So with 255 ticks, we can get that back up to, say, 100th of a second, or a little more than. So that's the max value you can get out of a 8-bit timer with the max prescaler of 1024. You can get it to 1/100th of a second. Now, as I mentioned, we're going to want this to run at, say, 1 second intervals. So, on for 1 second, off for 1 second. If I asked it for, say, 1/10 of a second, we get about 195 ticks. So what we can do is using those ticks to generate a cycle every to generate an interrupt every hundredth of a second, we can add an extra variable in there to count that interrupt, to count that tenth of a hundredth of a second to get the 1 second. I hope that all made sense. So, if we go back to the registers, now the timers are also used for PWM, that's pulse width modulation, which we'll talk about next time. And what we're essentially writing here is pulse width modulation, but when we talk about the actual pulse width modulation, you'll see it's a little different. So just bear with me here. So most of the register stuff is talking about setting up a PWM system. So we don't really have to care about that. Now for an 8-bit timer, the first register you're going to want to consider is the TCC R0A register. That's the control register for timer 0, register A. And what that will let us do is set up something called, if I keep scrolling down, CTC mode. Now we're going to set up an interrupt such that when the number of ticks matches the number of ticks we want, it's going to generate an interrupt. But what happens after that? We have to reset that timer. It has to go back to 0 so it can start counting up again. What the CTC does is that's clear timer on compare. So when they two match, it'll jump to the interrupt we have set up, and then it'll clear that timer for us. Nice and easy. So in here, we'll say TCCR0A equals, and then we'll shift 1 into the WGM, what did it work out to be? WGM 01 bit. WGM 01 bit. So, set CTC bit. Awesome. Now if we keep scrolling down to the TCCR0B bit, or register, that's the timer control register B for timer counter 0. So this is the second part of the AB register set. And again, most of this is still talking about PWM, but we get to here are the bits that control the prescaler. Now, if you leave this blank, the timer won't actually start until you give it a prescaler. So what we're going to do is we're going to say TCCR0B equals, and then we want, remember, 1024 prescaler. So that means we want to set CS02, CS02, and CS01. So one shift left into CS02, or one shifted left into CS00. Is that right? Double check that. Yes. Awesome. Okay. What we're going to have to do, though, is ignore that for a bit because we don't want it to start immediately. We have to set up some extra stuff first. So let's keep scrolling down. TCNT0, this is the actual timer. This is the thing that's holding the variable from, holding the numbers from the prescaler. So this holds all the ticks. OCR0A, this is the compare for A. We actually have two comparisons for the 8-bit timer. Each timer actually has two output comparisons. So you can have one for A and one for B. So you can actually set up two comparisons for only one timer. It's pretty nice. So let's just deal with our OCR0A. And this is what we set, OCR0A. And then we set that the number of ticks we want it to be compared to, which we calculated to be 195. 195. Okay, let's keep going down. Time mask. This is the register that controls the interrupts. This is where we can set, oh, when this happens, I want this to happen, this interrupt to occur. And this is the bit we're interested in, the OCIE0A. This is the bit that says, this is the bit that says, okay, I want an interrupt set up such that when my comparison value for A matches my timer value, it'll set an interrupt. So, So time mask 0 equals 1 shifted left into the OCIE 0A. And there we are. Now, if we read this, it says when the OCIE0A bit is written to 1 and the I bit in the status register is set, the timer counter 0 compare match A interrupt is enabled. What is this I bit it's talking about? Now, if you remember from last video, we talked about setting up interrupts. There's a quick way around it, and it just involves including an extra library called interrupt. And in order to set that I bit, all you have to do is say SEI, and that's a simple macro, and all that does is it sets that I bit, and I think SEI stands for set external interrupt. And so that sets that I bit. Now, is that it, or is there one? The TFR0. We don't have to worry about this because we're using interrupt, so we don't have to manually check the interrupt register. But all the TIFR0 register does is when that interrupt occurs, it'll set this flag here. So if we weren't using interrupts, if we weren't using an ISR, you'd have to check this manually. But because we're using that ISR, we don't. Pretty simple. Nope. So this just means start at 1024 prescaler. And there we go. Oh, there's one more thing we gotta do before we get into the ISR. DDRB equals OX01. And all that's doing is just setting the LED as an output so that we can see what it's doing. Okay. ISR, that's the interrupt service routine. This is the function that is called when the certain interrupt occurs. And that interrupt is called a vector. So this is timer 0 comp A vect. Now in the website I showed you last time, it has a list of all of these vectors for a given processor, in our case the ATmega328P, and what interrupt is occurring. And if you look that up, you see timer 0, comparison A, and that vector. So that's all in line with what we were talking about earlier. Now, this is set up, remember, to occur at 1/10 of a second. And we want it to go off at every second. No, not 1/10 of a second, 100th of a second. Sorry. We want it to go off every second. So what we need to do is say create an extra time variable. So when it's called, we'll say extra time. We'll increment that variable. Then we'll say if extra time is greater than 10, or no, not 10, 100. So this has happened 100 times. That's 1 second. Then port B, XOR equal 1 shifted left into the port B0. So all this little bit does is it says it'll toggle the LED on or off every 100 hundredths of a second, or every 1 second. And so that's it. So what we'll go ahead and do is build this, make sure everything's A-OK, make sure I didn't make any errors, good, and we'll open up our AVR Dude Assistant, we'll put this on the board, and we'll see what it does. Okay, so quick note before we start looking at what's going on here. I did have to make a slight change to the code. In that if bracket where I said I turn the LED on and off, you will have to clear the extra timer variable. You will have to reset it to 0. I forgot to do that, so I'll make a note earlier in the video telling you to do that. But yeah, and minor change to the board. I did have to add a tiny pull-up resistor, 10K, to the reset pin to make sure that this worked. I probably should have done that in my earlier boards. Didn't. You should do that now because it will screw with your result when you start trying to write other programs. Okay, now that restitution's made, let's talk about what's going on here. I've got the LED attached, and it is cycling at 1 second, which is what we wanted it to do, so that's working perfectly. Now, this is using 8-bit, and remember we did have to add that extra time variable, which again I screwed up, and I apologize for. So what you will have now, there is another way. Remember I mentioned the 16-bit timer. Now that's a lot more storage than a 8-bit timer. It's actually 256 times more storage. It's able to hold 65,336 ticks instead of just the Peaslee 256 we had before. So what we're going to do is we're going to go back and we're going to try and rewrite this code so that it runs with a 16-bit timer instead of the 8-bit. Okay, so opened up the calculator again, and this time I changed the resolution to 16-bit instead of 8-bit. And we're going to try and get 1 second out of this. And there we go. So with the highest prescaler, 1024 at a 20 megahertz clock, we're able to achieve 1 second with 19,531 ticks. Excuse me. So let's examine how the registers for the 16-bit timer. Now the process is exactly the same. We're going to set CTC. We've got to set the prescaler to 1024, and then we have to initialize a comparison value, and then we've got to set up the interrupt. So it's exactly the same. It's just the registers are slightly different. So if we come down here to registers, sorry, I've got the hiccups. Where are the registers? I know you're here. There. Okay, so TCCR1A. Again, it's like TCCR0A, except we're not going to use it because it's not necessary. This actually contains only the TCCR1A, only cares about the PWM stuff. I apologize again. It does have the WGM stuff we need from last time, but it doesn't have the right bit. TCCR1A only covers WGM11 and WGM10. When to enable CTC, we just have to set WGM12, so you can ignore TCCR1A. What you do have to take into consideration is TCCR1B, which does have the WGM12 bit we need, but it also contains the clock prescaler bits. So remember, if we leave these blank, it doesn't start until we give it a value. So to start with, I've gone ahead and created a new project. I'll include the interrupt stuff. And we'll put in the DDRB. So TCCR1B equals 1 shifted left to the WGM 12-bit. And we're going to ignore the prescaler stuff until later. Remember that when you set the prescaler, it starts the timer. Okay, so TCCR1B, we'll come back to that. TCCR1C, there's a C, but we don't care about that because it's still PWM stuff. Now, because this is a 16-bit timer and we're using an 8-bit processor, the counter, the thing that actually holds the ticks, is 2 8-bit registers put together. But again, because we don't have to reference it, we're using interrupts, we don't have to care about it. So we can just ignore that along with OCR1A, H, and L. That's the high and low registers. We will have to deal with that. Again, we're just going to be using the A register, not the B register. But just because it's 16-bit doesn't mean we have got to reference the high and low registers independently. Because we're using a very nice IDE here, all we have to say is OCR1A, and that will reference both registers in the proper order, and then we feed it the value we calculated to be 19531. Now we're using integers here because that's all you can put into 16-bit. It doesn't care about floating point, so just ignore it. I know that there's a 0.25 at the end, but that's fairly close within rounding. If it were like 0.75, I would round up, but it rounds down, so it's not going to cause a noticeable change in precision. Okay, so that's the reference number given. Now the mask. This is, remember, the register that controls the interrupt. So we say OCIE 1A, not 0A, 1A. OCIE 1A equals 1 shifted left into this case. Oops, got ahead of myself. Time mask 1. 1 shifted left into the OCIE 1A bit. There we go. Time mask is the register, not the bit. There we go. So now that sets up the interrupt. Then we write into the program SCI, set those interrupts, and now CR1B, we're going to say OR equals because we have to maintain the CTC mode. Now we can go ahead and set the prescaler bits to actually start the timer. So if we come back up, in order to get 1024, we set it to CS12 and CS10. So one shifted left into CS12, and then, oops, or one shifted left into CS10. Semicolon. There we go. So that's the setup we have. Nice and easily done. Now we can set the ISR, and the vector this time is timer1, comp A, vect. Now, we don't need that extra time because we're using the 16-bit timer, which will hold 1 second very nicely. And so we can just say port B, XOR equals 1 shifted left in port B, 0. And that's it. Now, we talked about the max time for the 8-bit. The max time for the 16-bit at the largest prescaler, 65336, is you can actually get almost 3.5 seconds out of a full 16-bit timer at the largest prescale. So that's pretty good. But again, we're just using 1 second here, but if you need something at 3-second intervals, use 16-bit at 1024 prescaler. So we'll go ahead, upload this to the board, and make sure that it does what we want it to do. Okay, so here we are, just uploaded the program, and we see that the LED is blinking at a 1 second interval. On, off, 1 Mississippi, off. Yep. So there we have it. So that's using 8 and 16-bit timers to run something pretty simple. Again, this is really close to PWM. It's not PWM. We will talk about that next time. But yeah, this is just using 8 and 16-bit timers to get an LED to blink on and off at 1 second intervals. So with that, I'm Human Hard Drive. Thanks for watching.